Hello, this is Dr. Nair, and I'm going to discuss Chapter 10 Organohalides in this video. We will again divide this into two sections. Um, First, we'll talk about preparation of alkyl halides, and then in the next video, we will talk about um, some of the reactions as well as oxidation and reduction in organic chemistry. Okay, so these are the few important topics that we'll be discussing in this chapter. Um, Organohalides are very widespread in nature and they find a number of uses. For example, the halogen containing compounds like trichloroethylene or methylene chloride, these have been used as solvents. And here we have some examples where they have found their use as a refrigerant in medicines, as a pesticide. Another example shown here is a sugar substitute. We are familiar with the sugar substitute called Splenda, and this is the main component of that compound, where sucralose, which has a carbon halogen bond, is much more, almost 600 times more sweeter than normal sucrose. Okay? Regarding naming the organohalides, we follow the same rules, IUPAC nomenclature. Just the only difference is that here we will also have halogens in them and we treat them just like substituents. Okay, so for example, in this case, bromine is just treated like a substituent, like a methyl or an ethyl, and you have to give the lowest number from that side of the chain, um, which will give you the lowest number to the first substituent. Okay, so these are examples which follow that. And also you have to arrange the names in the alphabetical order. So B comes first and then M, so that's why it's written as 5-bromo-2,4-dimethylheptane. Another example here, you can see we have two halogens in here. So again, they have to be arranged in the alphabetical order. B comes first and then the chloro and then the methyl. This is a example where we are showing the correct name and also the incorrect name. So the naming should be 2-bromo-5-methyl, just for the reason that B comes first and then M in the alphabetical order. A few haloalkanes which are more commonly known by their common names, like methyl iodide, isopropyl chloride, cyclohexyl bromide. Again, we can also name them as IUPAC nomenclature, like iodomethane, 2-chloropropane, or bromocyclohexane. An important feature of organohalides is that they have a carbon halogen bond, okay, and also that as we go down the periodic table, the size of the halogens goes on increasing. So the bond strengths, okay, going from carbon fluorine to carbon chlorine, then carbon bromine and carbon iodide, the bond strength keeps on decreasing, because bigger the halogen atom, it's easier to break the carbon halogen bond. Okay. Um, Again, as I said before, the polarity is an important part, bond polarity of carbon halogen bond, and carbon has a slight positive charge because of the more electronegative nature of the halogens, as a result of which the carbon in the haloalkanes is actually an electrophilic carbon. So we will see that nucleophiles can attack this carbon atom, and more reactions we will see in the next chapter. Now, for regarding preparation of alkyl halides, one preparation we have already seen in a previous chapter is halogenation. Okay, halogenation of alkanes. So you can either use chlorine or bromine to react with alkanes, like in this first step here. They have the different steps that they follow: initiation, propagation, and termination, and this is the overall reaction. Okay, so you can take hydrocarbons like methane, propane, butane, alkanes, and react with halogen in the presence of light, and you will get haloalkanes. Okay, however, this reaction actually is a chain reaction. So we cannot just make one organohalogen with it. It generally ends in mixture of products, because every time you can actually replace one hydrogen with a halogen atom. So if you replace one hydrogen, you get CH3Cl. Then if you replace two hydrogens, you get CH2Cl2. If you replace 3 hydrogens, you get CHCl3, and you replace all 4 of them, you get CCl4. So a halogenation of alkanes generally result in mixture of products. So this is not one of the best methods to prepare haloalkanes, but still it is a very common method to for us to use to prepare haloalkanes. Also, another feature with this reaction is that when the halogenation of alkanes is performed, you see that, for example, in this case, you have butane reacting with chlorine. You can see that there are 2 products formed here, and they are in the ratio of 30% to, or 30 is to 70. As another example is the 2-methylpropane, and you can see that the 2-chloro-2-methylpropane and 1-chloro-2-methylpropane, they are formed in the ratio of 35 to 65. Okay, and in addition, you will get more products like these ones, but if you focus on the previous example, you can see that when you are forming a primary alkyl halide, and if you see, the primary alkyl halide means halogen attached to a carbon atom, that is primary, and here a halogen is attached to a secondary. So this is a secondary carbon and this is a primary carbon, right? So it looks like the halogen prefers to be added to the secondary carbon atom than in the primary. And same thing, if you look at here, you see that the halogen is attached to a tertiary carbon atom, and this here it is attached to a primary. Now the ratio here is 35 to 65, which tells us that the number of tertiary carbon atoms is less as compared to the primary carbon atom, right? So that is the only reason that you're getting more of the primary organohalide. Otherwise, if you look, it is generally the tertiary carbon atom that is prone to be substituted with a halogen. Okay, this reason is that a radical stability, I think we had talked about this in an earlier chapter, but radical stability is such that the primary alkyl halide, the primary radical that is formed is less stable than a secondary alkyl halide radical, and that which is less stable than a tertiary radical. So the radical stability decides about the percentage of the product that is formed. Okay. So we can write down here that radical stability is in the order: a tertiary radical is more stable than a secondary, which is more stable than a primary. Okay. So generally the tertiary positions are the ones that will tend to be substituted first, and then the secondary, and then only the primary. Okay. Now another method of so here it is, the stability of the radicals here shown here. Okay. So this is a tertiary radical, this is a secondary radical, and this is a primary radical. Another method of preparation of alkyl halides is what is called as allylic bromination. Now allylic position is the position of the carbon atom next to the double bond. Okay, so for example, in this structure, okay, we have a double bond here. So the allylic position will be the position that's shown here. Okay, so this is my allylic position. Same thing, we have now this one is also the allylic position, and we have hydrogens here. And if these hydrogens are substituted by halogen, so if this is reacted with, say, halogen like chlorine, but this again has to be done in presence of light, then it is generally seen that the halogen is substituted at the allylic position, okay, or the hydrogen is substituted with the halogen here. So we do not substitute the hydrogens that are attached here onto the double bond, or even here. Okay, the hydrogen that is substituted is generally the hydrogen that is at the allylic position. Okay, so this type of reaction is called as allylic bromination. Again, you can look at this example here. The carbon atom next to the double bond, this is my allylic position, and they are these hydrogens here. Okay, there are 4 allylic hydrogens here. These are the ones that are prone to be substituted by halogen rather than any other hydrogens. Okay, so we can go into the details of this to understand why this happens. But again, let me draw out a structure here to show which exactly is the allylic position. Okay, so once again, see, we have a double bonded structure. Okay, normally if I had treated this with bromine, what would happen is the double bond is going to open up and you will get bromines attached to the double bond. Okay, but when you treat this same compound with NBS, now NBS stands for N-bromosuccinamide, and here what happens is it targets the allylic position specifically. So as we said before, these are the allylic hydrogens, so they get substituted by the halogen. And where are we getting the halogen from? It is from this N-bromosuccinamide, which is a slow source of bromine. Okay, so like in the previous slide, you see this is a N-bromosuccinamide and the bromine is coming from here and it is replacing the allylic position. Now let's draw out the different hydrogens in the same molecule, and I'm going to use different colors to address that. Okay, so we have hydrogens which are on the double bond, which is my blue hydrogens. These are called as the vinylic. Okay, so the blue hydrogens are the vinylic hydrogens. Then we have the allylic, which are my orange hydrogens. Okay, so these are my allylic hydrogens. And then we also have these hydrogens here, which are my alkylic, the green ones. They are the alkylic hydrogens. So when this reaction happens, reaction with NBS, okay, only allylic hydrogens are targeted. That means the orange colored hydrogens are the targeted hydrogens. These are the ones that I have circled. These are the hydrogens that are targeted, none of the other ones. Okay, so that's why we get the product here where the allylic hydrogen is substituted by the bromine, which is coming from our bromine source, which is N-bromosuccinamide. Now the reason why this happens is that the allylic hydrogen, when it is removed, it's again a free radical reaction. When the allylic hydrogen is removed, you get an allylic radical, which is the one that is more stable. And the reason why that allylic radical is more stable is because it can undergo resonance. Okay, so let's go back to the same slide here, then draw the resonance. Okay, so see this allylic hydrogen, when it is removed, you get an allylic radical. Okay, here is allylic radical, and it can undergo resonance where this goes over here, this double bond breaks over here with only one electron and the other electron remains here. So you get a resonance for the structure, right? So that stabilizes the intermediate, which is your free radical, and that is why you get the formation of this allylic radical. Okay? Whereas if you had removed this vinylic or the alkylic, there is no resonance structure. Okay, there is no stability of resonance structure. So therefore, allylic radicals are the ones that are easily formed, and this is the stability of the radical now. Previously, we had talked about primary, secondary, and tertiary radical stability, but now you see allylic radicals are the most stable. Actually, you can extend this to benzylic radicals also, which we'll talk about in another video. But you can see that whenever radicals or any compound can be stabilized through resonance, then um, that takes priority, right? So here, the reason why the substitution at the allylic position takes place is because the radical that is formed is stabilized by resonance. Okay, so you can see another example here. This is showing you a propene, all right? And same thing, if I had taken this and treated it with NBS, okay, it will target the allylic position, which is here, carbon atom next to a double bond. So you would actually get the product where the hydrogen at the allylic position is substituted by Br. So you can explain that the reason why this is happening is because the radical that is formed, which is my allylic radical, this one, it can be stabilized by resonance. See here again, you can show the stability of the radical by the two structures. The double bond goes over here and the radical is formed. Okay, so this is the whole reason why it, if possible, for the compound in allylic position is more preferred to be substituted. Okay, let's do another example. Now this is 1-octene, and when this one treated with light and NBS, we get a similar phenomena again, where we start by forming the radical, which is then it undergoes resonance to form a radical at another position, and you actually, in this case, you end up with two products. Okay, let me illustrate that with a different example. All right, so here we have let's draw the skeletal structure. Sometimes it's easy to see through that. Okay, say for example, I have this molecule, okay, and I'm treating it with NBS. So before we write the product, let's identify the allylic positions, okay, because that's where the substitution would happen. So again, carbon atom right next to the double bond is the allylic. So these two green hydrogens are my allylic hydrogens. So the first step would be where the hydrogen with this is removed, and you get the formation of the allylic radical, which is this one. Okay, but see, we can make the resonance structure of this. This goes over here, this goes over here, and this comes over here. So you get the double bond now formed here and the radical here. Okay, so these are the two radicals. Now, if the Br comes and if the Br radical forms bond here, then let's redraw the two radicals without any arrows. All right, so I'm going to redraw the two radicals. So we have this radical, the double bond here, the first allylic radical, and then the second is the where it has moved, and here. Okay, so these are the two resonance structures of the allylic radical. Now, if this radical reacts with bromine, again remember bromine is coming from our NBS, then you get bond formation over here. This will give you the structure, this one here with the bromine at this carbon atom. Or if the bromine decides to combine with this radical, right, then it will form a bond at the first carbon atom here, and you get Br here with a double bond. So look, these two are two different compounds. This will be 1, 2, 3, 4, 5. At the third position you have bromo, so this will be 3 bromo, 1 pentene, and this will be 1 bromo, 2 pentene, correct? So you end up in two different products because of the resonance phenomena of the allylic radical. So this is one method of preparation of alkyl halides. This method also has use because you can actually get sequence of double bonds, and we will learn about this in the next chapter, but just want to mention it here. Okay, um, this we can skip over here because it's asking you that if you have a structure like this and then you treat it with NBS, what are the different products you can form? So you will have to target the allelic positions again, right? And then form the different products. So you can see that since this is an unsymmetrical alkene, you will actually end up with 4 different products. First targeting these 2 allelic hydrogens, and then targeting these 2 allelic hydrogens. So that's how this has been worked out. All right. Then another method of preparation, we're still talking about preparation of alkyl halides, is from alcohol. Here we are not going to look at the mechanism. We'll look at the mechanism in the next chapter. But just to know that if you have tertiary alcohols, if you treat them with hydrochloric acid gas, HCl gas, then you can do substitution reaction. You can do a substitution of the OH with chlorine, and this works best for if it is a tertiary alcohol. Okay? So this is one of the most useful methods to make alkyl halides, but it generally works best for tertiary alkyl halides when they are treated with HCl. You can do it with secondary and primary, but it is slow, and the better method for using primary and secondary would be the either with SOCl2, okay, thionyl chloride, or with PBr3. So if you have a secondary alcohol, then the best method to replace the OH or substitute the OH with chlorine would be to use this reagent, which is called thionyl chloride, SOCl2. Or if you want to put a bromine over there, that means again it's a substitution reaction. As you can see, this is a secondary one. PBr3 works best. It's phosphine tribromide, phosphorus tribromide, and you can see that it is replacing the OH with the so remember, for the primary alcohols or secondary alcohols, the best way to convert them to alkyl halides would be to use SOCl2, or PBr3, okay, depending upon whether you want a chlorine or a bromine. And if you have a tertiary alcohol, then the best method to convert them into alkyl halide would be to use HCl gas. Okay, so we will look at more details of the mechanism in another chapter, but for the time being, you can remember this as a method of preparation. Okay, so far we have looked at the different methods of preparation, which are halogenation of alkanes. So let's list them out. Halogenation of alkanes, that's one method. Then we did allylic bromination. Okay, that's mainly for putting a bromine atom, allylic bromination. And then the third one is from alcohols. Again, remember, for the primary and secondary alcohols, it is best to use primary and secondary. It's best to use SOCl2 or PBr3. And for tertiary alcohol, the best one is to use HCl. Okay. You can do fluorine too by the treatment of taking an alcohol and reacting it with HF. But most commonly we talk about the alkyl chloride and alkyl bromide. Okay. All right. The last topic I would like to discuss in this chapter is about Grignard's reagents. Now, alkyl halides, this is actually kind of a reaction of alkyl halide, where you can take alkyl halides and react them with, so this is alkyl halide, right? We can react them with magnesium, where magnesium actually inserts between the carbon halogen bond, and we get a compound which is a very, very useful compound, which is called as Grignard's reagent. Okay, Grignard's reagent. It is a very versatile reagent because you can vary the R. You can change the R to be a primary alkyl, secondary alkyl, tertiary alkyl, an alkenyl, that means having a double bond in it, or an aryl, like benzene kind of, um, benzyl kind of structures in it. Okay? Um, so basically the Grignard's reagents are very good nucleophiles. You can use them as nucleophiles or as bases. Okay, so they're even powerful bases. So they find a lot of use in nucleophilic, whether reactions involving electrophiles and nucleophiles or in acid-base reaction. Okay, so the reason why that happens is its carbon halogen bond is again polar, because the magnesium tries to push the electrons towards R group, and it itself gets a delta positive charge and R gets a delta negative. So here carbon atom is the nucleophile, so it can attack other electrophiles, and also, like I said, they are powerful bases, so they can react with any proton source and give an acid-base reaction. Um, so for example, let me get a plain slide for us to discuss this. Um, so for example, if you have methane, right, in your reaction mixture, and if you have a Grignard's reagent, say for example, sorry, let's take a proton source, right, let's take a proton source, like say for example water, okay, and if you have a Grignard's reagent, say for example CH3 MgBr, right, because it's R MgBr, that's the general formula, and R can be any alkyl group. So we have put methyl here. So now, as I said, these are powerful bases, right? So any proton source, anything that even is a weak acid like water, the carbon atom is my basic carbon. So it takes up the proton, puts its electron here, and you can actually end up with CH4 methane, and then OH Mg, yeah, right? So you can end up in the formation of methane. So that means if you are not careful to remove any proton source from your reaction mixture, then the Grignard's reagent will be rendered inactive. It can become change into a hydrocarbon, and then it may not be very useful for us. Okay? So it is very important that whenever you use Grignard's reagent, you have to prevent any moisture to be part of the reaction mixture. Otherwise, the Grignard's reagent is quick to react with any proton source. Okay, so like for example water, or if it was an alcohol, the alcohols can also provide a proton, and it will react with them to form hydrocarbons. So these Grignard's reagents, they don't occur in living organism, but they are very good nucleophiles. Okay, we will see more of their uses in organic chemistry too. But here it is important for us to at least introduce this reagent here, so that when you become more familiar with its reactions in the next semester. Okay, so we'll stop here for this video and talk about oxidation and reductions in the next chapter. Sorry, in the next video.